You already know how to get into the teams. So pretty much I trust that you already have a bookmarked or the invitation you have accepted to join. Mickey, did we send invitation to all the people who registered?
Yeah, in the email register, all
Yeah.
has been added.
Okay, nice. So that means you already have it. And in case if you don't have it, you can always copy this and keep it to yourself. That's this link. Cutly. This is a short link. If you keep it and bookmark, I think you should be good to go. Please share this here. All right. Those are the quick logistics. So as usual, we'll get started with some technology side to learn newly, followed by deep dive into learning Magma bits and bytes, right? So that's the thought process of this session. And I believe today we are in the fourth session of 12 session series. So the thought process here is, as a team, what we wanted to really do is we wanted to, build our expertise and work together to learn how different pieces come together to deploy a private networks or a fixed wireless access networks, right? So that's the thought process. But in order for us to really get there, which should be towards the end of uh, the 11th or 12th session agenda, we need to understand the very basics. So we kind of started talking about different basics, and we were trying to learn what is the difference between wireline networks, wireless networks, and we are going to continue to learn wireless networks, some additional things today and in subsequent sessions. Then we will also try to learn how additional technologies outside of wireless networks come together and help us to have a solution, right? And a use case that we can go after or learn and deploy to our customers or build products within our company. So we'll look at different adjacent technologies around that. And what's more important is a little bit understanding of standards and open source plays a role in today's era, and as well as last but not least the spectrum, right? So these are all some of the things that we wanted to really learn at a very high level while we are trying to deep dive and learn more about Magma bits and bytes. So now what is it? Magma, we know it's a converged core network, 4G and 5G converged core network. So we would, in the last sessions, what we did was, in last session, what we did was we Yokesh and their team, they presented an end-to-end call using the simulators for 5G. And moving forward, what they would be doing is they'll try to dissect that end-to-end call into smaller pieces, starting with registration and explain you bits and bytes of registrations, followed by the next procedure, and we will go through that process for next 4 to 5 sessions, and then we will turn ourselves into an end-to-end uh, you know um, end-to-end mode, meaning how this core network gets connected with the radio, connected with the BSS system. How does this whole end-to-end things work? And we'll have some representatives, volunteers will show demo from the end-to-end point of view as well, right? So that's the thought process. Now, continuing on that journey, in our last session from the technology point of view, we talked about end of the day, why do we have this 5G and in future 6G as a technology that's available for us? Is mainly it's all about stretching the KPIs and leveraging different technologies to solve the customer challenges. So that's the most important thing. The world is moving towards the connected, intelligent world, programmable world. Um, you know, Analytics and AI embedded, automation embedded. A lot of things that can happen automatically without the manual intervention. So those sometimes they're called as a closed loop automation. Sometimes it's called as a self heal, self XXX. Let's put it that way, right? So that's the direction that we are moving forward, and our thought process as well as the learning skills have to adapt to those new world, and we got to develop our expertise and upskill ourselves to adapt to that new world so we are able to provide innovative solutions to our end customers. So on that context, what we also looked at was end-to-end network at a very high level, right? Logical level. It starts with the air interface where you have multiple devices that connects to the radio, and then the radio connects to the core network through some transport network. So that's pretty much at a very high level that we looked at it. And we started getting into the depth of different types of networks, and we finally ended up with the architecture of a 5G network. What are all the different components that makes up the 5G network? One thing, if you all remember that I was telling you, from one technology to another technology, we went to converged mode. In other words, integrated mode, then we went to distributed mode, then we went to converged mode, then we go to distributed mode. I mean, but end of the day, the bottom line is what we wanted to do is we wanted to create openness, and we wanted to create the intelligence, right? So when you create openness, um, and automatically the innovation happens. The intelligence becomes part of what you do. And that's end of the day was the vision of an operator, whoever is deploying this network. The vision of theirs is I don't want to be tied to one particular vendor, and I want a solution that is multi-vendor, and I want a solution that is disaggregated so I can deploy the different components where I need, depending upon the use case that demands my network to perform in particular way, right? So that's the key message, and the 5G is basically catered to or ground up built to really do that. And we started understanding about 5G architecture in our previous session. You can always go back to the previous recording and you can look it up. And we talked about two types of networks, right? Standalone and non-standalone networks. So non-standalone is all about how do you leverage the 4G core network. Standalone is all about how do we, leverage the newly defined core network with the new radio to achieve not only the broadband use case, but also mission critical and IoT use cases. So moving on, we also looked at different types of architecture, service-based architecture and traditional architecture. And we also looked at different new components that are added into the 5G network architecture. This is what we kind of discussed in our last session, which kind of helped you to understand at a very high level what the core network is all about, the differences between different types of technology core networks, and how the 5G core network is different from the 4G core network in architecture, and also in the way that it addresses the different use cases and customer challenges, right? How it addresses person to machine communication and machine to machine communication, whether it is a business critical, mission critical use cases that you are trying to deploy. Now that's from the core network point of view. But if you take a step back and if you look at just core network doesn't make up this 5G network end to end, right? So you have a radio network, you have devices, and then you have a transport network. Today, before we deep dive into Magma, what I'm going to talk to you in next 10 to 15 minutes before Yokesh takes over for next 35 minutes explaining the Magma registration flow is to help you understand a little bit on the radio side, right? And if time permits, maybe we will talk a little bit on the transport. If not, we would probably stop at the radio side at a very high level. So you're able to understand the, start understanding and expanding out of core network to get to an end-to-end view. Okay, so that's the thought process. Now let's move forward. I'll pause here for any questions or any comments from anyone before we move on to the radio network. No? All good? Perfect. Right. So let me go on to this slide. So what you see in this slide is the radio network. Now, if I go back to this previous one, which just a minute. So what we basically did was in our previous session learned about the core network. Now what I'm going to really talk about is the radio network, and then that is relevant for 5G. So I wanted to directly, instead of going back to traditional radio network and then showing you the evolution all the way to the virtualized LAN to the cloud RAN, which we anyways saw at a very high level in the network evolution from 1G to 5G in the previous slides. What I'm going to do today is directly jump into ORAN. So what is ORAN, right? ORAN is by name it says O stands for open. RAN stands for radio access network. right? So what you see in this slide is the architecture of Open Radio Access Network. And why Open Radio Access Network? I go back to my same statement that I started today with. Openness enables innovation. It enables, the different things that you can do traditionally to a more intelligent way of doing things, right? And also it brings in, particularly Open RAN, it brings in embedded AI with it, right? So these are all the, these are all the things that operators really, really needed. Okay, so that's the thought process, right, of ORAN architecture, and it's all about intelligent openness and embedded AI within the RAN network is nothing but Open RAN at a very high level. So what you see is the architecture of the Open RAN. So if you think about Open RAN, I'll put it in a very simple way. It's easy to understand, right? So what happens is you have an air interface, right? So you have a spectrum, and a company, let's say an operator acquires a spectrum, and there are devices that supports that spectrum. So that devices are connected to a radio network, and the radio network also supports that spectrum, right? So that's how different devices gets connected to the radio network. Now, when it connects to the radio network, the first thing that it connects to is an antenna, right? It's called as an RU, right? Radio unit, the real antenna that you see. If you look at the buildings, you would see that radio unit, right? So that's the RU. Now, what happened in olden days was that that RU also had, in 2G, it's called as a, PSCs, and in 3G, 4G, it's called as, you know, um, what is it called as? Anyways, it's not coming into my mind, but you understand, right? So you have all these different components together. But in the ORAN, what they did was they kind of split this into multiple different smaller pieces. So the operators can deploy different pieces in different locations depending upon the use case requirements. So the one that you see in the bottom is the radio unit RU, right? So then RU is connected to the DU. This is the next connection. So this DU, let me put it this way. So the RU, DU, and CU. Think of an OSI stack, right? OSI stack has a physical layer all the way to the application and presentation and session layer, right? So like that, the radio stack also has a different layers, starting from MAC to RLC all the way to the RRC, and in between PDCP and so on, right? So it also has a different layers, and in other words, it also has a stack. So now what they did was they kind of created different functions that supports different layers of the stack. That is all it is all about, right? So that way you can actually disaggregate the network. So in other words, I'll show you, I have another slide. You will understand very clearly what I'm explaining. But the bottom line is, so RU supports, for now you understand, bottom one layer of the stack, right? The physical layer. And the next one is the DU, which supports next two layers of the stack. Right? What it is, I'll show you in a pictorial way rather than saying it. You'll understand that better. Then you have on top of that CU that supports next to three layers on top of that. Right? So they kind of divided that radio stack into multiple network functions that supports different layers of the stack. So that's how they kind of disaggregated and created this Open RAN architecture. They call it as an RU, DU, and CU. And the CU is further split into control plane and user plane. I'll talk about it, what it is, right? So you know what is a control plane? It's just a signaling messages. User plane is the user browsing, talking, and doing stuff, right? So they kind of split that into two portions, CU as a control plane and user plane. And the most another important thing is they introduced two new components. The one component that you see here is a near real-time RIC. They call it as, right? So this is what is an embedded AI powered radio control. So AI can make decisions on what radio should do depending upon the data that it analyzes and the instructions that are given automatically or manually, right? So that is near real-time RIC, and then non-real-time RIC. So the RIC is, radio intelligent controller, which is nothing but your AI-powered analytic engine, right? But now the RIC is divided into two components. One is the near real time, another one is the non-real time. So non-real time functions like policy, service creation, all those things that you can do it in this block, right? And the real time, making the decision, enforcing the decision, is something that you can actually do it in the near real-time rig. For example, mobility control, and other applications that are require near real-time decisions to happen, right? So just to give you that picture, this is the high level, right? Just think 2 points. The radio stack is divided into multiple different network functions like RU, DU, CUs, and then they introduced two components, that is near real-time rig and non-real-time rig. Near real-time rig is for the real-time functionalities, and non-real-time rig is non-real-time functionalities. RIC is nothing but radio, intelligent controller. Now, it's that they divided all these into different functions. All these different functions has to be connected through different interfaces, right? And then they started defining different interfaces. What are the different protocols that has to go between these two different interfaces, and why is all the standard is being defined for that, right? So that's at a very high level, 5G logical architecture of Open RAN. Now, this is a little detailed way just to give you with an example, mostly focused on the rig side of it. So in the non-real-time rig, in the top right, you can see its policy, configuration, services, all those kind of activities you can actually do. In real-time rig, you can even install the third-party application that does some intelligent service assurance of the radio network. Just as an example, mobility management, QoS management, those kind of things you can do it in the real-time rig, because these are all the things you have to decide in real time and adapt your network so you can provide the services that you intend to provide from your RAN network. So those are some examples. That's why this particular diagram I kind of presented here. Then the bottom one is pretty straightforward. You know that you have a physical layer, and then you have a couple of layers, MAC and RLC. So this is your DU, right? And this diagram, this is your DU. Then you have in your CU control plane, you have RRC, which is the signaling messages, right? And user plane, you have PDCP and SDAP. SDAP is the one that does, mapping of the uplink and downlink into internal logical DRB, right? Radio bearers. So if you know the radio technology, you would understand what I mean. But at a very high level, the SDAP is the one which kind of maps the uplink and downlink from the outside world to the inside world, right? At a high level, you can think something like that for your understanding purpose. So this is what is the ORAN architecture at a very, 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 very high level. Okay. Now I'll go one step further down. So you already know now the RU, DU, CUs, all these different things has been designed in such a way that different pieces of the radio stack can be supported by all these different devices. You already know that. Okay. Now each of these different devices does certain functions. It's same as any other stack, whether you take TCP/IP stack, right? Ethernet layer, what does it do? Right? MAC layer, what does it do? IP layer, what does it do? You know that, right? So likewise, different protocol layers in the radio stack does different things. So my intention is not to really go through in detail what each of these different slack layers in the radio stack is responsible to do. But at a very high level, two things that I wanted you to take away and go today, right? One thing is different functionalities of that's supported in the stack is being disaggregated and developed as a different network functions, right? Which is RU, DU, and CU. And in some cases, the DU and CU also is further split into high DU, high CU, right? Kind of a thing. To even further split some of the functionalities so you can disaggregate to its fullest. Now, the complexity of disaggregation depends on your design of the use case that you depends on the use case that you wanted to design and support, right? In some use cases, you can have everything together, the complete stack together into one single small box or a virtual machine or a container, right? Within the OpenStack or Kubernetes. Or you can split all these different pieces, put it into the different virtual functions and containers, and connect all of these different things located in different places in a way that you can offer the use case to your customers. So those are the two key messages that I wanted you to remember out of this particular slide. Now, most of the time, what happens is when you talk to any radio expert, they will talk about, hey, which option are you? They might ask you, hey, first thing is what spectrum? Spectrum is something that we will learn in our later sessions, right? But the other thing that you will always hear from the people is, hey, I mean, which option do you support? Do you support option 1, option 2, option 7, option 8? I mean, let me tell you, this is no magic, right? If it is option 8, all the stacks other than the radio stack, everything is inside one device, which sometimes called as VBU, right? And if it is option 2, then it is a CU, DU, RU split as an example, right? If it is option 7, then it is an RU and CU/DU split. So if you I kind of put an example to split as an example, option 8, option 2, and option 7, right? But you can split it in 3, 4, 5, 6, and everything, depending upon your use case, and you can support it. So that's the key message that I wanted to really give you. Just to summarize before I hand over it to Suresh, Yokesh and team is, Open RAN is all about creating openness and intelligence and embedded AI into this. And it's all about disaggregation of the radio stack into different network functions so it can address different use cases. And those disaggregations can come in multiple forms. And depending upon the use case, which form is mostly suited, you would choose that. And most of the cases, I have seen option 7, but it's not mandatory. Depending upon your use cases, you can choose whichever option that you would need, provided the RAN vendors support that kind of option as something that they sell to you, right? That's the most important thing. And end of the day, what's going to happen moving forward, right, with 5G and 6G? This is just a high level view to share it with you guys. RAN, most of the RANs that we have known of is basically, is structured as a cells, and each cells covers X amount of users, and you architect and design it in a way that you support that, right? So that's how most of the radios are architected nowadays. But moving forward, and in some cases even today now, right, it's going to be a dedicated radio for a particular device, right, through beamforming technology and MIMO processing. If you don't understand what is beamforming and MIMO, don't worry about it. But the bottom line that I wanted you to understand is that in order to provide a high data throughput, high low latency, low jitter, to support the mission critical applications, moving forward from a device sharing, a multiple device sharing, one common location and one common bandwidth, to one device dedicated to having one defined dedicated bandwidth that can be offered not as a best effort but as a dedicated QoS, will result in a lot of different new use cases. So that's pretty much I wanted to cover for today. As a summary, so now what we have understood from the technology point of view, you know the core network, you know the RAN, you know the device, right? These things comes together. There's one missing piece at a very high level that you need to understand. What are the different technologies that come together for transport is something that we will discuss in our next session, right, in 2 weeks. So with that, I will pause here and see if Yokesh and team is ready to get started with their session for today.
Yeah, Katha.
Good. So let me.
Yeah.
So far you learned big picture, and now you're going to deep dive into bits and bytes and message flows, parameters, and so on. So we wanted to kind of balance this 1 hour session between these two things for all the sessions that we plan to do moving forward. So with that, Yokesh, floor to you. Please feel free to share the screen. You have your 35 minutes to go over your session.
Okay. Yeah. Yes. Is my screen visible, Katha?
Yes, I can see.
We'll just start with a quick recap of what we did last in our last meeting. So this is the website, Wavelab's website, where we have put the procedure on how to enable Magma, which is the 5G core, and how to get it integrated with the other open source like OAI. So this OAI, or Open Air Interface, they provide the GNB and the UE simulator. So here we have mentioned on the steps. What are the so if we go inside it, we'll have a Vagrant file which tells how many CPU, how many cores is going to require, and then the launch commands. So this basically tells how is the topology, what are the commands it needs to get to Magma up and running, how you can insert a SIM, basically, how to get a SIM registered with the core. Uh, so there are commands for it. And then, how to go to the latest software version of Magma. Uh, so this is it. And then we have the equivalent commands for OAI and GNB core. I'm sorry. Uh, so here we have told how to launch the Dockers, how to launch the the GNB and the UE simulator, and all the configurations are inbuilt, so you don't have to do any other stuff. Like just take two virtual boxes, make sure that Ethernet connectivity is there, like by pairing, and then all the IP addresses and other things are all inside it. So and of course, your machine should be pinged to should be connected to the internet because it pulls a lot of packages. So yeah, I think if there are any questions, comments, let me know, or you can post it in this channel. If you face any issues, you can put it in the issues channel, or you can connect us via Slack, or there are a lot of other options. Um, so that was what we did last week in our last meeting. So today we are going to do a little bit more deep dive. Uh, Target is to have only registration. Like when you switch on your phone from airplane mode to the regular mode, and then you see the bars over there, which will say like right now it will say 4G VoLTE. But once this the GNP and other tools are there, it will start showing 5G, which means you are connected, your phone is 5G enabled, and you are latched onto the 5G network. There are a lot of procedures involved from UE to GNB and from GNB to AMF. Mostly we are going to see the right hand side where AMF is involved. This is for the GNP part. If time permits, maybe in this session or subsequent session, I'll just try to give a high level overview. But what we are mostly focused on this section on how GNP detects UE and how it gets registered with the network core, the AMF part of it. That how actual browsing takes place, how a session is created, all these things will take it up in the next section and next presentations. But today it is just how a UE gets itself registered with a service provider, how it gets authenticated and validated, and it is ready to use the network. We are mostly focused on that. So what we are going to cover, some registration flow, some very high level configurations. As you all know, we are in telecom world, we mostly use SCTP protocol, and then some logs, registration call flow, and some recaps. So, as a, UE gets, when you make it from airplane mode to normal mode, or you just start up the UE, first of all, it will get registered itself with GNB. Then GNB will, either it will be pre-established or it will establish on a need basis. It will create an SCTP connection with AMF. And then, the initial handshake. So first of all, GNB will get it registered with AMF. So some initial handshakes, so GNB will tell its capability on similar lines. AMF will accept, reject, whatever, based on certain parameters. And then, assuming that GNB is registered, GNB is accepted, then GNB will start sending the UE specific information towards AMF. So that will be so the whatever you see here, the NGAP part, it mostly deals with the GNP side of the communication, and then we have the NAS part, which mostly deals with the UE related stuff. So assuming GNP is registered, all good. Now the UE will be actually registered with the AMF core. And then, we will have all the other components, the subscriber DB, where you will have pre-configured information, policies for what kind of bandwidth or policies you need, and then the pipeline D, which will actually give you the fast path. So this is a flow on a high level. So first, GNP gets registered, and then it sends the registration information of UE towards AMF. Yeah. Uh, uh, there are a lot of configuration files I would accept, but so all that most of them are set to default. In case if you want to tune certain things specific, we can tune it. But all the default configurations you can see here. Maybe in one of the slides, the very specific configurations which is needed, maybe we'll highlight it. But this is where you can find all the YAML files which are read to configure all the required parameters. Yeah, so we were talking about the SCTP connections. So by default, Magma comes up with 4G and 5G. So if you see 36412, it is for 4G, but mostly we are interested in this 38412. This is mainly used for 5G connection. So if everything is healthy, if all our installation went through fine, we will see a SCTP port ready to cater to the GNP and UE on the 5G part of it. Right? If the GNP connections are up, you should see certain entry in this SCTP associations. I think we don't have to worry much about it, but I'm just, for sake of clarity, completeness, we are covering it. So this is mostly on the SCTP, the initial handshake between the GNP and the AMF, which will be shown. These are the various loggings we have. We have MME log and syslog, where MME log just converts the 5G specific. So we will mostly concentrate on 5G. So it have all the registration, PDU session, all the messages which are related to AMF. And then we have a second set of logging, which is called syslog. So anything apart from MME goes into syslog, the fast path, session management, policy management, all of the logs, we can see it in syslog. So MME logs for AMF, which is supposed to capture the UE and the GNP, and then the syslog for the rest of the device. Any questions till now? I think if I just maybe during starting it might not be required, but as when we start more and more deployment, more and more hands-on, I thought those are the points which we should be aware of. Any questions till this point?
No, all good, Yogesh, all good. The intention is to really get into this kind of details to understand the Magma core in your session. All good. So far, so good, at least from my end. If anyone has any questions, please feel free to.
Yeah, so I think we'll move. If there is any question, maybe we can take it in the end, or you can post in the chat. So this is the main registration flow, call flow. Of course, there are a lot of other possibilities, but we are just capturing the first all positive scenarios. There are a lot of negative scenarios also to be handled, and there can be slight variation, but this is the most regular call flow. So CPE is your customer device, so it can be your UE or any other device. RAN is your GNB, which is the radio node. And then we have MME or AMF, which will cater to the registration radio station establishment. And this is the subscriber DB. Subscriber DB in the sense, once you get your SIM, it will take some time to get it operational. So what happens in the background, your operator is going to burn out the entries specific to your SIM, your authentication, and other details here, and then only it will get activated. So as soon as we switch on our phone, the registration request is sent towards RAN. RAN then encapsulates the message with some additional informations and forward it to MME. I will, in subsequent slides, I will just show you what are the main components here in registration. So this is the request which comes in. Then this request, we have to validate whether this is an authentic subscriber. So then we ask our subscriber database that this UE or CPE device has asked me for the details. Can you provide me all with the credentials or authentication mechanism? Then the subscriber DB shares the authentication mechanism, and it tells whether it's a authentic user. And then what MAV does is it asks CP to authenticate itself. It sends an authentication request with some kind of challenge, and then the CP or the device has to provide the response. So it has to solve the challenge. It then comes back again to MME, and then what happens? The AMF will ensure the response is what is expected by the subscriber DB. So it kind of matches whether it's in line with what is entered. So assuming everything is good, then it sends a security mode command. So security mode command and complete. So basically, in case it will tell the level of security you need with the handset device. You want it to be encrypted, unencrypted, or what kind of integrity algorithms that has to be used. So everything is provided in this security mode command and complete. So assume that both has agreed on what kind of mechanism to be used. Then AMF sends a context request to the RAN. What is this context request? So AMF will tell to the RAN that this handset is acceptable, and these are the bandwidth parameters. These are the uplink and the downlink bandwidth. You create a context and allocate that much bandwidth. So then RAN will say, okay, all good. So it will send it back. And then once this is done, then AMF will send the whole registration is accepted. So that means you have the authentic user, and all the required bandwidths, the default bandwidth has been assigned to you. And then CP said, okay, from my side also, everything is okay. And the registration is complete. So once the registration is complete, after this point, CPE is allowed to use the network for browsing the internet or for whatever reasons. It then becomes an authentic user to make use of the services provided by the operator. So just on a high level, first is the registration, request, then authentication, then security mode on which kind of algorithms are needed, then allocation of bandwidth from the RAN and the context creation, and then the final accept message to say that the handshake is complete. So this is a flow on a high level. So this is the actual packet capture, meaning whatever we see here, we can find the equivalent captures here. So the first two messages are for the GNB registration. like, it is just as soon as GNP is powered off, it will set up the SCP channel. From the third message onwards, it's all the UE request which is coming. So you can see the initial registration, then authentication request response, then security mode command complete, and then the registration accept and registration complete. With this as the initial context setup, because basically this is where we were telling that GNB also have to allocate resources for the U. So some messages can be piggybacked or as per TGPP, they can be independent also, they can be piggybacked also. So we try to piggyback as much as possible so that the number of packet exchange is less, but this is one set of packet flow. So after this, we have this PDU session establishment. For now, we are not covering it, but just to give a high level, that the last three messages is to actually set up the actual connection and then start using the internet. So that we will cover in the next in the upcoming sessions. But apart from the last three, our idea is to just show till registration complete. Okay. Of course, there are a lot of terms involved, but what I would like to do is I will just touch upon the very identifier which is used very commonly across all these procedures. We have tried to show it here as well. One is this MSIN. So your IMSI, the SIM card which you got, it will have, like, let's say India Airtel. So they will have country code and the operator code. And after that, this MSIN is your specific identity. So you will be like, okay, this is for Yogesh Pandey. This is the SIM which has been given to Yogesh. And then there are a couple of identifiers. Some of them are provided by RAN to identify the subscriber, and some of them provided by the UE. So the ones which are provided by or allocated by RAN is called RAN UE ID. And for AMF, it is the AMF UE ID. So RAN has its own identifier to identify the subscriber, and AMF has its own identifier. So you can see this RAN ID allocated by RAN, AMF ID for identifying the subscriber, and the MSIN, the specific SIM to the user. And then we have this most important feature called TIMSI, TMSI. So what happens? We don't use the IMSI all the time, because we can have a man in the middle attack, and we can it can figure out that what's going on. So what we do is, for this specific IMSI, we give them a temporary identifier. So after that, what happens? The SIM card will not use its IMSI number, but it will always use this TIMSI number. And this also gets periodically updated. So it's only during the initial handshake we use the SIM identifier, but other than that, we always use the temporary identifier, which is provided to the SIM by AMF. So of course, there are a lot of other identifiers, but these are the ones which will come across as and when we are setting up our basic registration flow. So once again, MSIN for the specific IMSI, TMSI is for the temporary identifier, RAN UEID is allocated by RAN to identify the subscriber, and the AMF to give an identity to the UE from the AMF side. So yeah, this is just to show what are the high level components in the messages. So first is the initial UE message. So basically, this is the first time when the UE is powering up. It will share its identifier, its capabilities. Is it the first time connection, or is it a subsequent connection? Has is the security already security messages has been already established. All these kind of initial handshake or initial information messages will be provided by the UE in the initial UE message. So here is the all the capability identifiers and the security related stuff here. Moving on to the next message. This is the authentication request. So as soon as we get the registration request, we go to the subscriber, fetch all the details, and then then AMF poses a challenge to the UE with authentication vector and random vector. So this will be sent towards the UE to authenticate itself. So we have AMF has a pre uh, uh, knows the response expected response type which we are going to get for this challenge. So this challenge is sent towards the UE for authentication, and using the 3GPP spec 5G AKA algorithm, UE is going to solve that challenge and will provide a response, and then AMF will validate is it the expected response. Assuming all good, UE is authenticated and is the correct is able to identify itself. Then we will exchange the security algorithms to be used. What kind of encryption, integrity protection, all these kind of algorithms will be used. So prior to it, it will be pure plain message without any security. But after the security mode is accepted, everything will be as per the agreed algorithm. So this is the message sent by AMF to UE. It will respond back with its capabilities or the acceptable types that, okay, we agree on to this algorithm for integrity or encryption. All good, we are in sync. So after that, that's the final handshake, which says registration accept. So that means everything. So this will be sent by AMF to UE saying that all good from my side. And then, okay, maybe I think we missed the last message. There is a message called registration complete. So that will be a final completion message from UE that all good from his side as well. And then the session is ready to use. Again, we have our same kind of demo. I will just quickly show you the main components, but this is the setup we are having for demo. We have an orchestration where you can configure the subscriber with all its authentication. This is where AGW, access gateway, where Magma and the EMF component is running. These are the GNB and GUI simulators. And the idea is they should register themselves and then they should be able to use internet. So the sending of the data part is for subsequent, but for now it is just that how we are getting registered. So these are some of the 3GPP specs which we follow. So there are spec for how GNB connection should be made, how EMF connection, how the UE connection should be made, what are the procedure for authentication, what is the procedure for sending the data traffic. So everything we have captured here. Of course, again, it's not entire, but what are the first set of things which you can look relating to this registration. We have captured it here. Just as a quick, maybe going to 3GPP spec as a starting point might not be a good idea. Maybe these are some of the blogs which you can go through, you can get the understanding, and then for details, you can, of course, go back to the 3GPP. But these are some of the quick references we can go through to show that, to get the initial understanding on the messages in this. Yeah. Any questions? Otherwise, I have a demo. I will just quickly go through on the high level procedure. So whatever I explained here, I can correlate. I can show it in the log so that while you are playing with the installation and bringing up the session, We can correlate with those logs to see how it goes. So I think this is the entire video, but I'll just skip. I'll just try to fast forward to show the critical portion. So this is how this we covered in our last discussion, how to start the services, and then once your services are up, what are the commands we can use to see if things are working. So Magma status, this is the command. It shows all the processes, their state, uh, and their health and other things. So it takes a couple of seconds to launch MME because all the dependent services should be up before MME comes up. So it will take a couple of seconds for MME to come up. So yeah, now it is up. And again, we can confirm the status with this command, sudo service magma @MME status. So this will show you the status, whether it's active running. These are the prerequisites for this to start, uh, and some of the other details. The logins are initialized, the sessions are open. Uh, yeah, so this is the command to validate it. This is the ports, SCTP ports, which I was mentioning. This 38412 is to tell that we are up and running for the 5G services, and we are ready to take any connection. Yeah, so this is like before GNP connects to us, we are showing that we are ready to make it. So one is started to listening on the port. This is for we are ready to make the associations. So these are some of the logs which we discovered, which we discussed. These are the syslog. So these are the non-MME logs which can be used, like pipeline D, session D, all the session management and policy management stuff will be captured here. And then we have MME logs, which is used to capture all the registration procedures and all the AMF, UE, GNB kind of interactions. Everything will be captured here. Okay, so here we are ready to capture the packet and start our simulators to show that all good to go. Yeah, so I think this is the TCP dump. Whatever packet capture we have shared in the PPT. This is actually taken from this when we were capturing this demo. This is again a quick recap of the last session. This is the procedure to launch a GNP. Yeah, so this is to show that SCTP, we have received SCTP connection from the GNB, and we are ready to the GNB is registered with us. This shows the PLMN, like this GNP belongs to which PLMN, like the country code and the operator code. So it basically validates whether things are properly configured. There's no mismatch. Yeah, I think not sure if you're able to see, but the command which we showed association. So if GNP is connected to us, you will see the entries. So the left hand side and the right hand side. So the left side will be the Magma, and the right hand side is the GNP IP. So that means the association is up and running, and we are ready to take on the new UE. Okay, so. Yeah, so these are the this shows the interface which is used for the connection. Okay. Now we are going to launch the UE. Again, this was captured in our last session. So yeah, this is just to capture some of the. I mean, not everything is captured here, but some of the things like no encryption message. So that means this is before our security map has been exchanged or agreed. Then some of the security procedure which is going on. We are going to highlight them. So this is basically one, you can see it from the PCAP, and second, how to map the PCAP with the logs here. Yeah, so this is the command where we have received the initial UE message, which tells that UE wants to register itself with this X amount of capability, possibility with these identifiers. And yeah, it's the registration type, uh, the request which we receive, and then this highlights the authentication request. This is a challenge which AMF sends towards UE, which tells that this is the challenge from my side. If you provide a response and if it is expected as what is there stored in my database, I'll accept you. So the authentication response has been received. Yeah, and then this shows the security algorithms, integrity algorithm, or the encryption algorithm, which has to be shared. In this demo, we have used only integrity algorithm. We have not used encryption because if we use encryption, then it will be difficult to show the PCAPs. So for this video, we have just enabled the integrity algorithms. These are the security mode commands. Um, and then the security mode is completed. And it is the last leg where we say registration is accepted. So it basically ensures that, of course, then there are some context setup which we share it with GNB, because GNB also has to allocate the resources for the specific UE. And then we have this registration complete. Okay, so I think this was the main procedures we want to show. Some of the logs might need to be disabled. The default logs are info. To get this additional logs, we have to, in the YAML files I showed, we have to enable it for the debug mode so that you can get the additional information. So some of the logs you might not see once if you are bringing it for the first time, but we can change the mode to get all the details. Any questions from anyone? I know it was difficult to get all the pieces, but the idea was not to go in detail, but to show what are the steps which happens as soon as our phone is switched on. And then once the registration is accepted, you will see the 5G signal in your phone.
I think it's a very, very good session, Yokesh. I mean, we are anyways going to post this YouTube, right? And most of you all know where to go and get access to. You can just search Wavelabs YouTube or Desktop or YouTube. You will find all these videos. But I think from my point of view, it's a great session. Would encourage if anyone has any questions to ask. On my end, I have a doctor appointment that I just need to go out, but feel free to stay back and discuss if you guys have any questions. Um, Wonderful, Yokesh. Thank you very much for your time, energy for the session.
Thanks. Thanks a lot.
Khader, I think there is a question on the chat.
Okay,
But
Pedro.
it's
Hey,
from
Pedro.
Pedro.
How are you?
Yeah, Pedro, I think some we have some configuration for sake of demo we have taken. But we have used this OAI labs, OAI thing. We are using this OAI simulator.
Yeah, so what I think the Pedro is asking is these configurations or out of the box configurations that we can put it in the CPQT lab, or is it something extra that you have done to make this automated, right? So that's the question. Okay.
Yeah, I think maybe Pedro was asking, this is it is 724, it is for Brazil MCC. So
Yeah.
I think it was, yeah, meaning we took some, we used the Brazil as a country code.
Yeah, yeah, yeah. Yeah, definitely, Pedro. I think in open source, every different organizations have their own USP. So I'm sure that every company in the community is adding certain things that would differentiate them from what you would normally see it in the open source that's available, right? So there may be definitely different people would do different USPs. Maybe Yokesh has some magic done it to keep his USP. I think I don't know, but I'm just sharing the general norms. Yeah, Pedro, understood. Your mic is not working. Thanks for joining, Ahmed. Thanks for joining. Everyone, thanks for joining. Is there any other questions? We know you, Pedro, by the way.
In terms of the time taken for the registration, how quick it is with 5G as compared to the previous predecessor technologies, and also in terms of resource requirements, how expensive it is as compared to previous generations. Any info on this?
How would you like to identify yourself? Where you work?
Yeah, my name is Shravan. I work with AMD here in Markham.
Okay. Okay. Hey, Fahad. Yeah, good to know you. Yes, Yokesh, I have my own answer, but yeah, please,
Sure.
Yokesh, if you have an answer, go ahead.
Yeah, meaning Shravan, I think meaning registration procedure with compared to 4G, I think most of the pieces are there. Like of course, some information is meaning it will not. We can't compare what is fast and slow, but most of the pieces are similar to what is there in 4G. So they are comparable, but meaning authentication security mode happens in 4G also. So there is not much difference. Of course, what happens in 5G, you can encrypt the IMSI also, like the first MSIN which I showed. So then it will be little delayed because there is an additional time for decrypting it. But otherwise, you should not see much difference between the 4G and the 5G authentic registration procedure. They are almost on similar lines. And regarding the resources, so meaning Regarding the resources, like, we will use meaning GNB. So it will have its own bandwidth and frequency. Meaning, or your question was with respect to that, or if I understood it correctly?
Resources, when I say any the ability on the UE side in terms of processing capability or the memory requirements. So any additional demand from 5G to 4G transition.
Yeah, meaning on the UE side, there will be definitely, because the authentication mechanism is little different. So that has to be this thing. And then, as I mentioned, we have an additional encryption algorithms in 5G. So that will increase a little bit on the UE because there are five uh, different key combinations we can have, which was not there in 4G. So those are called SUSI encryption. So it will be a little bit more, but not, it will not be a very huge difference. That's what I would say.
I
see.
mean,
Okay.
my answer to that, right, is how you look at it, right? So from the point of view of signaling performance, and from the point of view of user plane performance, right? Definitely there is a difference, right? And particularly in the user plane performance, that's where if you look at how 5G is different from 4G, you would actually see, right? 5G supports more throughput, low latency. There's some background noise, not sure. Can you guys also hear the same background noise, or?
Yes, correct. I think.
Okay, no worries.
Yes, there have been background noise.
Okay, so end of the day, obviously we know the difference theoretically from 4G to 5G, right? It's going to allow us to not only person to person but also person to machine, machine to person communication, supporting many use cases on the critical mission critical communications as well. So obviously it has to be faster from that point of view, right? That's one way of looking at it. The other way of looking at it is um, the actual difference between the number of messages that goes back and forth between 4G and 5G, and the time it takes, is their attach rate, the differences between 4G and 5G. That's another metrics that we can actually look at. But those metrics mostly on the signaling side, right? But most of the 5G provided metrics is all on the user plane, like latencies, jitter, throughput. They're all on the user plane side. So there's various technologies on the radio side that allows you to do that, right? We talked about beamforming at a high level and so on. And from the stack point of view, also it has to be little. In some cases, it is little heavier. In some cases, it little lighter. But again, it depends on how you are architecting your RAN, right? You can have a disaggregated RAN we talked about. And if you look at the stack point of view, in 4G we just had PDCP, and 5G you also have that, what is that called, SDAP, right? Some additional layer there. So there's always a difference between 4G and 5G. But what's more important, the way that I look at it is, if the user plane meets the 5G requirements, um, for instance, throughput, GDA, jitter, that's one side of it. The other thing is on the control plane side, if you're able to do 1 million of devices within a square kilometer, which is what 5G is talking about, right? So keeping so many devices and handling so many devices on the control plane side, if you're able to do these two things, I think we are better off in 5G compared to 4G. Hopefully it answered your question, if not to its fully extent, but at least it answered your question, I guess.
Yeah, that's right. Yeah, it did, Kader. Thanks.
Awesome. Okay, so guys, I think we can take a break. We are 11 minutes over time for today. Let's take a break. You all know how to join the session in 2 weeks. Looking forward, all of you joining this session, and we will have some exciting new topics that we will learn. And I've sent my LinkedIn For those who are not connected with me in LinkedIn, in the chat, please feel free to connect with me. Chat offline. You live in Markham. Let's meet up. I'm traveling right now on business, but I'll be back mid first week of May. So we'll meet up as well, Fahd, right? You said Fahd, right? What did you say? Your name? I kind of missed it. Maybe. Yeah.
Me, my name is Shravan.
Shavan, right? But it
Yeah.
shows why it shows a different name. I don't know. In the teams, Shavan. Yeah, let's connect, Shavan. Let's catch up. Would be
Yep.
interested to share knowledge and see how we can collaborate and learn together. Thank you so much, guys. You all have a wonderful evening, morning, afternoon, weekend. See you guys in 2 weeks. Take care. Bye-bye.
Thank you.